Yeah. My name is M.V. Chari. I am President Jindal Urban Waste Management, and we are operating two waste to energy plants. And this plant purpose mainly for the salvage of solid waste, municipal solid waste, where we are taking near about 1200 tons to 1400 tons of waste per day, near about 15 to 20 urban local bodies or municipalities, and we are generating per hour 20 megawatts. This solid waste management is a burning subject. Not only this, this particular plant has been visited by 2,500 students in 50 months of operation, and it basically addresses all kind of subjects like thermodynamics, civil engineering, next strength of materials, refrigeration, air conditioning, and combustion systems and statometry. This one. So now, as per the request of the principal from Vikas, now I am entering into this subject. Not only that, I am requesting all the faculty members to listen my lecture very carefully. I have also added extra protocols like I am member in expert advisory committee in Department of Science and Technology for a period of 3 years. I am also visiting faculty to IIT Kharagpur, IIT Delhi, and Administrative Staff College of India to teach solid waste management subject to IAS officers and various senior officers of the urban local bodies. Not only that, I have recently got the membership in Waste to Energy and Research and Technology of University of Columbia Earth Engineering Center. Now, coming into the subject, I have traveled extensively various countries. Mainly, I was very much attracted the way the Chinese are progressing towards the development. In China, the industry and the university, they are working very closely. In one of my experiences earlier when I was in the iron and steel department to work for my project in Jindal in Bilwara unit, where we have given iron ore investigation to Sinosteel. Sinosteel inwardly given the investigation and prototype investigations through Hangzhou University. Those people, they totally characterized the iron ore characterization. Based on that, they built and designed and engineered a plant of capacity 1.2 million tons. Now, coming to this subject, we are also inviting your faculty to visit our plant and understand. And we have also taken a lot of initiatives for the students' understanding of this one. Before that, the lectures also, they have to visit the industry. They should understand how the application is working in the uh, particular plant in operations. In this particular plant in operation, suppose if a civil person, a department from civil it comes, they can do in the initial stages of project the survey and shifting of mean sea levels and fixing of temporary benchmarks in the site. Not only that, the contour maps, grid maps, and the meteorological conditions also can be done from the university. When I worked in the Lanco Industries near to the Srikalahasti, Rachagunneri village industrial hub, we have invited the SV University's lecturers to design our shed like truss columns and all these things and civil foundations also. So this theory is a bit difficult and application is very easy. But there is a lot of gap between the theory and application because the universities are not involving in the industry. During my tenure in Department of Science and Technology, many IIT faculties, they used to come and they used to present because as an expert advisory committee member, we identify the projects submitted and we give the grant. In that process, we have given a grant of near about 150 crores to various projects. For example, banana tree is there. That banana tree, from that sanitary napkins making and some residue materials are there. Like in our plant, there is a bottom ash and fly ash is there. This fly ash and bottom ash we have given to PhD Technology College. They did a research and ultimately they given a design in such a way that this bottom ash can be converted into paver blocks, can be converted into solid bricks, and convert into construction bricks or something like that. And not only that, this research is underwent to use this bottom ash as a subways for the formation of highways. When the lecturer knows the application and how it is practically working, then there will be a lot of enrichment is there so that this lecture can practically explain the students. Particularly if you take a subject like mechanical, civil, electrical, instrumentation, automation, in the university, you cannot build all the labs in the university. It is highly expensive. The best thing is you have to define the fundamentals to the students. Even if you teach many students how the resistance appears, many people they don't know. How the capacitor appears, many people they don't know. We have prepared a manual in the industry in such a way that, for example, if you take our waste to energy plant, that is Jindal Urban Waste Management Guntur Limited, in that I have instructed my electrical and instrumentation department and automation department. First, you identify what are the items are available, whether it is a transformer, whether it is a breaker, whether it is a current transformer, whether it is a potential transformer, whether it is a motor, or different kind of things. Let them capacitors, battery chargers, inverters, like that. They identified that one, and based on that one, they practically, if you, what is its application? Suppose if you take a transformer, what is its application? If you cut inside, what is inside? How it functions? What is the precautions to be taken? These are all most important things. For your information, during my childhood, when my study has taken place in Nagarjuna Sagar, we are blessed. There, we used to see the films from Soviet Union, where the school children's, for the creativity purpose, they used to make the small cars, small equipments, a battery charged vehicles, motorized vehicles, something. That gives me a lot of impact in my childhood. It was enriched by particular imagination and creativity, understanding of the requirement, understanding of the function and all these things. As long as if you teach the theory, students cannot understand. That theory will grow when they come and visit the industry, then it is equally important for the faculty as well as equally important for the students also. When they come and see the reality, what is happening, and their understanding and ultimately the passion towards the subject will terribly enlighten. Once they feel that it is so important, then they will understand the need of the subject and how it is useful to the society. I am giving you one important aspect to you. If you take Netherlands, the Netherlands is 50 times smaller than India. And the land available for Indian mass is 50 times more than Netherlands. And our land is highly fertile, whereas Netherlands land is less fertile. But what makes the agriculture products export? Netherlands exports 38 billion US dollars of exports to the other countries, whereas India is 50 times bigger than that Netherlands, but we are exporting only 18 billion US dollars agriculture exports. What it makes difference? It makes difference is they are using the technology in the agriculture, in the watering system, in plowing system. You see, India is a country of many population. It is there. For example, I will give one example. Since we have a population to create jobs, for example, a traffic police is there, standing in the hot sun, and he directs the vehicles and all these things. This is not the giving job or something. It is a great strain to the human being. Instead of that, the same person create a cabin at the junction and he should monitor through lighting system and Then he should operate that lighting system. Once green light, one direction if you operate, vehicle should go. Other direction, if we put red signal, the vehicle should start. It improves the efficiency. Then how you will realize? When you know the real understanding of the things you know. Next, all the most important things for civil engineer. In Vikas Engineering College, the nearest, the biggest masonry dam in the world is Nagarjuna Sagar. I don't know how many of your faculty and students have been visited that Nagarjuna Sagar dam. It was started in 1955 and the project was real start pylon. It was laid by the Pandit Jawaharlal Nehru, Honorable Prime Minister at that time. In real sense, it is started in 58 and the project has been completed in 68 in 100 crores. And this project, it is built not out of concrete, it is built out of simple made from the masonry work. And it is serving today 20 lakh acres of the land for agriculture through mainstream, left canal, right canal, and the total amount of hydel power it is generating near about 1200 megawatt. If you see physically how the students' passion will increase towards engineering. This faculty, once he understands, then he can motivate the students. For your information, I also worked for some time in Usman University as a part-time lecturer. I completed my AMI, I have not completed BTech or BE. During that period, as a part of our survival, we used to go as a part-time lecturer to take the payment. But I have seen the labs inside Foundry and all these things. But the infrastructure facilities, what it is created is just to understand what is the minimum facilities. But in larger scales, if you want to understand, it is most important that we have to go and visit physically. For example, in Guntur district, it is a lot of cotton which will grow. In the crop season, labor is not available to pluck the cotton flowers, to take out the cotton and all these things. So if you mechanize it, then there will not be any issue. Whatever the manpower is available, we have to improve the skill. Unless the faculty knows the skill by understanding with industry, with their subject of in-depth knowledge about the theory, then they will have a way forward how to teach the students and all these things. So coming back to the point, particularly if you take our industry, we are playing the presentation to you. First, you understand the presentation. How I understand the presentation? Because I, as a part of, though I have 30 years of industrial experience, I visited various places, seen many waste energy plants. Then I come to know what are the merits and demerits in the industry of this one. And we have created a lot of data bank, which is on the ground reality because I have seen the plants. Now I am giving the presentation. You kindly see the presentation. Please share the screen. So today the topic is solid waste management in India, particularly in Andhra Pradesh. Next slide, please. This is the waste generation in India, and we are processing very less. And the waste generation per capita generation, it is 200 grams in rural areas in India, 500 grams in urban areas. But international norms of United Nations is 1000 grams. Okay, you please see today the waste generation, it is 62 million tons. By 2031, it is raising to 185 million tons per annum. Next. Already we don't have proper disposal of waste, so years together we have dumped the waste into the dumps. That waste, it is called legacy waste. As on date, this waste, it is lying near about 1300 million tons, where CPCB has did the survey for 3000 sites, and in 2030 it becomes 1400 million tons. At the same time, daily generation of municipal solid waste, it is near about 160,000 tons. As on date, in 2030 it is becomes 200,000 tons. In 2050 become it is 330,000 330,000 tons. This, if we have some kind of knowledge, we can convert into energy. The subject relevant, it is thermodynamics, basically 100%. Next, the impact of dumps. It is also, we have collected preparation from the IICT and many international forums. We collected the data. If you dump 1 ton of waste in the open dump, the methane generation is 150 kgs and carbon dioxide generation is 2000 kgs, and methane is 21 times more dangerous than the carbon dioxide, and NOx is also, it is coming, but in this particular process it is very less, and the land required, it is 2480 acres. The academy, if you work in this direction, they can develop a models so that they can find a solution. And not only that, since it is a mixed waste where biodegradable waste and dry waste all together, there is a liquid, it leaches from the municipal solid waste, where you kindly see the BOD, COD and TDS. It is all are higher limits. So a civil engineer can also address a water kind of treatment plant, where if the civil faculty comes, he can see in the industry how this leachate it is processed and we are generating the waste to energy. Once this water goes into the ground, it pollutes the groundwater decades together. We have done one case study at Hyderabad. In Hyderabad, there is a place called Jawahar Nagar, where the dump is to be there earlier. There about 50 lakh tons of dump it is there. There, the leachate is secreted into the ground. From Jawahar Nagar, if you take as a center, and 50 kilometers in and around, whatever the water, if they drill, the water coming, it is in a dark color, and that water cannot be used. Next. This next, please. Out of our experience, we have addressed like that municipal waste, the best technology is mass incineration. I am going to explain. The existing dumps, it is called biomining, where we can generate refuse-derived fuel. This fuel can be used as a substitute for the coal. In India, the thermal substitution, it is only 4%. Whereas government of India, it is planned to take it near about 20%, something like that. In European Unions, the thermal substitution means that is the main fuels, and the fuels generated from the waste, it is reached up to 40%, 50%. This is the thing. Next, there is a wet waste. That is, we are throwing food. In one of my lectures, when I given in some of the universities, the food waste per annum, it is 22 billion US dollars. That much food we are wasting. And this food, if you throw it outside, we are losing a lot of energy, something like that. Similarly, vegetable waste. Okay, from vegetable market, fruit waste from fruit market, flower waste from flower market. This all the best process is biomethanization, where we can generate biogas. This also a case study for the chemical engineering students, where they can do study and generate a model of digester. Whatever biogas, if you filter it we can reach it methane 99%, where it is, if you compress it, it becomes CNG. That is called, it is called bio-CNG. And lot of slaughter waste also we are throwing out, and we are polluting the environment. This also we can use digester and we can generate biogas. So in this process, the university also, the faculty can work in the direction to generate a model. Because I personally seen some of the digesters in Hyderabad, some of the digesters I have seen Bangalore, where from fruit waste they are generating biogas after filtration. They are using as a fuel, as a substitute for petrol. Similarly, I have seen vegetable market waste in Hyderabad, Boyenpalli, and this flower waste I have seen in the Gudimalkapur. I physically seen with my eyes. And after that, this paper I generated. How I got this knowledge? Because I visited the working models and note down and prepared my articles and everything using my theoretical knowledge of thermodynamics and all these things. And we are doing a lot of construction work, and just like that we are throwing. Okay. And whatever this construction C&D waste means construction and demolition waste, whatever it is doing, if you use a mechanism of crushing, magnetic separation, screening, this can be used as a sub-base for the formation of national highways, where we can save the gravel. In reality, to form 1 gram of gravel in nature, it takes 950 years. And another most alarming thing it is happening today as on date. Many hospitals, they are just like dumping the biomedical waste as a normal waste, which is really very dangerous. In 4 years back, what has happened in Guntur, the drainage pipeline and drinking water pipeline moving side by side. Because of the corrosion, both the pipes are got punctured. That water was taken by the local people. Near about 11 people, they died out of diarrhea and another diseases and all these things. So the best technology is plasma. This also university can study thoroughly once they understand the physically come and see the industry. Next. This is the present technologies and future technologies, because the technologists will never satisfy with this one. In the process, they tried for gasification, pyrolysis, thermoselect, and plasma and all these things. So I am explaining that one so that in future, in one of your subjects, you can enroll, and not only that, you can physically see. This is all the basis is thermodynamics only and physics also. Next. This is the gasification. After gasification, what is happening? We are generating syngas. The composition is, I have given clearly, hydrogen is carbon monoxide, carbon dioxide, and nitrogen. Next. This is the pyrolysis. Pyro means is fire. Lys means separating. And we have given a definition, what is the percentage of oxygen. In absence of oxygen, whatever heat it is generated, that is called pyrolysis. Next. This is plasma. If you take the fire, it is a plasma. Ionized atmosphere is also called plasma. This is very much suitable for the medical waste burning, incineration, so that the harmful effect of medical waste can be mitigated. Next. This thermoselect process in some of the European countries, they have tested and they tried. We have to appreciate their effort because it is under R&D. For example, how the coal it is formed, how the fossil fuel is formed. This petrol, diesel, all fossil fuel is formed from the dead bodies of the different kind of creatures in the nature. And this coal it is found because of the pure vegetation of the these trees and everything. There is a term called in geology subsidence. In subsidence, what happens? Because of the earth movements, a big earthquake comes, then the total forest goes into the earth inside and it is buried by the gravel and all these things. In years together, because of the pressure and temperature, first peat will be formed, after lignite will be formed, after that bituminous coal is formed, and finally anthracite is formed. So on that basis, they taken that principle and tried for the municipal solid waste, but it is not succeeded. Next. We have given a comparison statement between gasification, pyrolysis, plasma, thermoselect, and incineration. And today, we have decided that the incineration is the most acceptable technology. This particular presentation, I will ask my lecturing in charge, Mr. Ramakrishna, to share it to you separately. Next. Next. This is the total money invested on the latest technologies. Near about 4 billion euros they destroyed. You kindly see Siemens pyrolysis process. They established 2 plants, but ultimately they closed. One role, neonal gasification, thermoselect gasification, MGC gasification, all plasma. These technologies, they worked for some time, but not in a continuous manner, and commercial viability also not achieved. Next. This is the photographs of the technologies where the latest technologies failed. You can see the photograph inside. Next. This is also another failed technology. Next. This is also photograph of another failed technology of our latest concept basis. Next. This is thermoselect. This is also measurably failed. The total amount in European Union destroyed is 4 billion euros. But to some extent, these technologies can be used in other where this hospital waste, plastic waste can be mitigated. Next. Ultimately, if there is no incineration, no emission, no residue, there is no success. But these latest technologies, they claim that we incinerate, but there is no emission. There is no residue. It is not possible. If we take human body, we take food, we take water, and ultimately it converts to some energy. Rest it goes into the form of stool, some part it goes into the form of urine for purification of blood and all these things. So when there is an incineration, there will be emission. When there is an incineration, there is a residue. Without this, the technology cannot be a success one. For that purpose, we have explained like this. Next. And this is purely RDF. It is meant for the legacy existing dumps, where, for example, legacy waste. What is the definition of legacy waste? If you characterize the legacy waste, it is 20% will be plastic waste, cotton waste, and wood chips mixture is there. Rest is totally gravel. Now, what is the RDF, refuse derived fuel? If I process 100 kg of legacy waste and we receive only 18 to 20% of refuse derived fuel, the characterization of refuse derived fuel is 80 to 85% will be plastic waste and 10 to 12% will be the cotton and wood chips are there. Okay. Some of the metals are there. They remove it. It is to a tune of 2%, 3%. There we clearly explain what is the percentage of metals and what is the percentage of paper waste, wood waste, and other non-ferrous material. Ultimately, the recovery, they are saying that 33% something, but in reality, it is less than 20%. This refuse derived fuel can be used as a substitute for coal if it is properly processed. Next. This is the mass incineration. You will show you the video also. Next. Mass incineration is highly friendly as when we discuss about the pollution matters. Suppose if you take a deep forest, there is no pollution. But the day the human activity starts, the pollution will be there. We cannot avoid pollution, we can control pollution. We have established two waste energy plants in Andhra Pradesh. One is in Guntur, one is in Visakhapatnam. The emissions we are following as international standards. This we have shown for various forums to indicate that these particular plants are highly friendly environment, and some of the plants are set up even in the city center where we cannot set up a coal-based thermal power plants in the city center. Next. This is our plant data. Both plants are in operation for Guntur plant 52 was, Vizag plant 48 was. Till to date, we have received 17 billion tons of MSW at Guntur, 15 billion tons at Visakhapatnam, and we have consumed near about 16 million tons at Guntur and 16 million tons at Vizag, and the units generated, it is near about 562 million units we have generated. This it is generated totally from waste. If you take the Andhra Pradesh electricity consumption per day is 200 million units. This 52 months plant running can support 2 days of the state power requirement. And in this plant load factor is also very high as compared to coal-based thermal power plants. In coal-based thermal power plants, plant load factor can be achieved only 78%, something like that. And whatever bottom ash it is generating at the boiler bottom, and whatever fly ash it is collected from the back filters. This also can be utilized, and your civil department also can collect our ash samples and can they do research how this ash can be used in the construction field. Next, this is the bricks we have made out in tie-up with PSG technology, where that PSG technology, they are more interacting with the industry. That is the reason they could able to find some solution. And another, whatever leachate it is coming, where civil department faculty has a lot of attraction, we are generating the drinking water out of this leachate. Next, we are showing the plant video. It is 4 minutes video. Kindly see the plant video. Please display the plant video. This is the plant video, and ultimately My only request to the universities or engineering colleges, the faculty should work very close to the industries. I am giving one simple example. Engineering drawing is called engineer's language, and many engineering students they don't know how to work on engineering drawing because there is a chapters like projection of points, projection of straight lines, projection of the planes, and projection of solids, intersection of surfaces, isometric views, and perspective views, and all these things. For your information, in one of my drawing teacher, he is asked me to make projection of hexagon, hexagon, solid, prism. Next, pentagon, pyramids. He used to ask to do this with the cardboards. We did that. You come on to the front face. We did that. Similarly, these intersections of surfaces are development of surfaces. Today, in most of the fabrication industry, the building of tanks, building of ducts, laying of pipelines, everything it comes from the development surfaces of the engineering drawing. The drawing teacher, the mechanical head will teach engineering drawing. But in the industry, in a project execution, how this engineering drawing is applicable. And many people, they don't know what is the scale, 1 is to 20, 1 is to 200. That scale, they don't know. And mechanical, also the assembly drawings, many people, they don't know. Civil also, building plan, they don't know. Suppose if we want to prepare the layout, we need to have a lot of inputs. After that, only the layout can be made. So ultimately, my request to the faculty or university and the heads of the universities or heads, the principals of the colleges, they have to push the faculty to the industry to work very closely and work in such a way that use their theoretical knowledge to generate concepts. Once concepts is generated, the equipments can be made. I am very thankful for the Vikas Engineering College for giving me this opportunity.
Yeah, dear participants, actually due to some network issues, the resource person is unable to connect now. So, if you have any queries, you please keep in the chat box. We will convey to the resource person. If you have any queries, please keep in the chat box, and we'll convey to the resource person. And afterwards, the next session will start, and resource person will come. So please keep your queries if you have in chat box, please. Any queries, dear participants, please keep in chat box. Otherwise, we'll switch over to next session. Okay, thank you, Dr. Ankita Saini, ma'am. Thank you for your question. Rishi Kumar Shukla, sir, thank you for your question. sir. We'll surely convey these questions to the resource person. Okay, dear participants, thank you for your queries. And next session will be by Dr. S.V. Vinod, sir. Sir Vinod, sir, are you there, sir? Dr. S.V. Vinod, sir. Dr. S. Vinod, sir. Have you joined, sir? Dr. S. Vinod, sir. Okay, we'll wait for the speaker to join and then we will continue the session. Dear participants, please wait. The speaker resource person will join.
There is a government school caste institution.
Pawan sir, good evening. Vinod here. Am I audible?
Yes, sir. Yes, sir. Vinod, sir. Am
Sir,
I
am I
audible,
audible
sir?
to you?
Yes, sir. Yes, sir. You're audible, sir. Sir, good evening, sir. My name is Ashwini Kumar, sir. I'm the coordinator, sir. Am I audible, sir? Sir Vinod, sir.
Sir, am I audible?
Yes, sir. Yes, sir. You're audible, sir. Am I audible, sir? Hello, sir. Sir Vinod, sir.
Sir, your voice is audible, sir.
Okay, sir. Sir Vinod, sir, I will first of all introduce you, sir. Then I will hand over the session to you, sir. Okay, dear participants, coming to this resource person, Dr. S. Vinod is a professor in production engineering department of NIT Tiruchirappalli, Tamil Nadu. He completed his PhD and master's degree in production engineering from PSC College of Technology, Coimbatore, and bachelor's degree in mechanical engineering from Government College of Technology, Coimbatore. He was a top ranker in his undergraduate and postgraduate studies. He has been awarded National Doctoral Fellowship for pursuing research by AICTE, New Delhi. He has been awarded with Highly Commended Paper Award and Outstanding Paper Award by Emerald Publishers, UK for the year 2009 and 2011. He is the recipient of Institution of Engineers Young Engineer Award for the year 2013 to 14. He has published over 200 papers in international journals. He got featured in world ranking of top 2% scientists, both in career-long and single-year categories, released by Stanford University, published in PLOS Biology based on research publications, number of citations, and H-index consecutively for 5 years since 2020. He is on the editorial review board of various international journals in the specializations of manufacturing and industrial engineering. His research interests include lean production and sustainable manufacturing, agile manufacturing, additive manufacturing, product development, and Industry 4. So this is the brief introduction about today's resource person, Dr. S. Vinodh. Sir Vinodh, sir. So I'm handing over the session to you, sir. Please share the screen and carry on, sir. Please unmute.
Am I audible to you? Am I
Yes, sir.
audible?
Yes, sir. Yes, sir. You are
Let me
audible,
share
sir.
the content. Yeah. Let me share.
Please share, sir.
Okay. Is the content visible?
Yes, sir. Yes, sir. Visible, sir.
Okay. Is the slide movement clear, sir? Is the slide movement clear?
Yes, sir. Yes, sir. Changing, sir.
Yeah. Okay. Shall I proceed? Yeah.
Yes, sir. Carry on, sir. Sir, maximize, sir. Maximize.
Yes, one-
Presentation mode, sir.
Just
Okay,
one
sir.
second. One second. Just a second.
Yes.
Is it fine now?
Yes, sir. Yes, sir. Fine, sir. Please carry on, sir.
Okay, fine. Yeah. So good evening, all. It gives me pleasure to be a part of this ATAL FDP program. So this session I'll be focusing on the concepts of smart and sustainable manufacturing. So I shall just proceed with the discussion on smart manufacturing concepts, then further sustainable manufacturing, and we shall discuss about the significance of these manufacturing systems in the present industrial revolution. And the faculty and members and the attendees of the session can post your queries in the chat box. And interimly, let us spend some time on responding to your queries, and then we shall proceed further. So with this note, I'm just proceeding with the discussion. As we are all aware that the industrial revolution has crossed like 4 versions, and presently we are into the 4th industrial revolution, also referred by the term Industry 4.0. And equivalently, it's called like smart manufacturing, wherein the present industrial revolution has a range of interconnected automated systems, which involves the fusion of physical, digital, and biological scenarios. There were a lot of developments that has happened, and the challenges had been faced in the prior revolutions, where the developments have taken place in computers and information technology, and also the scope of the metal handling and storage and retrieval systems, and the concepts of flexible manufacturing and computer integrated manufacturing had taken place. Ultimately, across the revolutions, we could understand there exists the need for developing the flexible manufacturing systems and enabling the intelligent manufacturing. So if you see the need across these, the emergence of the systems and also on smart manufacturing, there had been challenges being realized in terms of dealing with complexity, customization, and the global scenarios and the customer expectations in terms of diverse requirements. And the digitalization of manufacturing system is very much essential, and also the connectivity both horizontally and vertically, and the integration across the manufacturing entities in the system is very essential. And typically there had been a lot of changes that have been happening, and the interaction has to be realized in terms of material, product, and process phenomenon. And those three entities are very important even in the context of like sustainable manufacturing system. So the smart manufacturing system is based on three important dimensions: one on human ingenuity and utilizing the human intellectual ability and information, and further on technology. So the need had been realized for a quite a longer time in terms of developing more automated and technology-oriented system. And there were incremental changes happening across the operational practices. And typically, the manufacturing complexity seems to be higher. And there exists need for a real transformative manufacturing approaches, which are very essential in the context of integrating data, knowledge, and information technologies that were not prevailing during the prior time frame. Also, there were challenges by manufacturing organizations in terms of survival, in the terms of global competition. And there were like a lot of uncertainties in terms of market and dynamic requirements. And typically, manufacturers have to adopt innovative strategies in order to fulfill the requirements of customers and for survival in the competitive scenario. And the developments in terms of the higher levels of agility in product and process development. So the customer preferences are diversified and they are increasing, and also the global competitiveness is very a vital aspect. And in line with these developments and the changes, the prediction of the manufacturing system is also very crucial. And all these practical challenges could be reasonably handled and could be very well dealt through the emergence of smart manufacturing. So now it is more interesting to look into the four versions of the industrial revolution, which happened over time frame and which is very essential in terms of dealing with manufacturing competence. The first version started with mechanization, utilizing the mechanical and steam power. And the second version is about like electrification, utilizing the concept of assembly lines and mass manufacturing. The third version is about utilizing electronics and information technology to enable autonomous manufacturing. And presently, we do have the fourth revolution, which is based on the concept of cyber physical systems, Internet of Things, and other related technologies. Ultimately, the focus of the fourth revolution system is to enable a smart factory. So in this context, the term Industry 4.0 originated from German industries, and equivalently in the context of US, the concept is referred by the term smart manufacturing. And there are the term seems to be synchronous and the goals, but there were some operational differences as well, which we'll be discussing in due course of the session. So ultimately, the terms Industry 4.0 and smart manufacturing, they refer to a class of technologies which are based on the CPS, Internet of Things and Internet of Services, to develop a smart factory. So here, typically, every physical entity has to be supported with a virtual scenario, and typically digital twins need to be developed for the deployment. And typically, over the Internet of Things, the CPS communicate and cooperate with each other via IoT and iOS, and they are being supported with several other technologies in order to enable the digital revolution. And the role of sensors and other related entities are also equivalently important. And AI also helps in a big way to deal with the challenges happening in the context of a smart factory. And there were several challenges, and one of the important challenges is the development of a typical technological infrastructure, which is very, very essential in terms of deploying a smart manufacturing system. And it is interesting to note the concept of CPS, which forms the base or foundation for this the fourth revolution system, which has like entities, computational entities which can control physical entities, and they are the physical systems, and their operations have to be monitored, coordinated, and controlled, and they have to be supported using a computing and communication core. That's why in the context of CPS, 3 C's are very, very essential. One is computation, second communication, and third control. And thereby, the scenarios of the physical and digital perspectives could be monitored and could be regulated. So the concept of a factory, based on the prior versions, is that when we look at the perspective, the workstations are mostly rigid and they are little flexible. And we do have the robots which can help in going ahead with the manufacturing task, mostly doing some autonomous type of activities. And the system is rigid and it doesn't have like flexibility and adaptability to the varied conditions. But the scenario of the present smart factory is that typically the workstations are flexible and they are adaptable. And we could see the robots, mostly they do collaborative type of task with human workforce. Thereby the workstations could be typically configured and reconfigured rapidly. Thereby it can become a highly flexible and versatile system to deal with the requirements of today's factories. And in this context, it is very essential to understand the design principles governing an Industry 4.0 system or smart manufacturing system, where the interoperability is the CPS ability in terms of coordinating human and smart factories to connect and coordinate with each other through IoT and iOS. The second is about generating a virtual scenario of the smart factory, which can link the sensor data with the plant models. And the third is the CPS ability to facilitate autonomous decisions which is in contrast to the centralized scenario which happens in the traditional factories. And the fourth is about the ability to collect and perform data analysis and derive inferences very rapidly. And the fifth is about the service orientation supported with iOS. And the sixth is about flexible adaptation of the smart factories in line with the requirements of individual modules. So these 6 design principles are very, very essential for configuring a smart manufacturing system. And the development of digital twin is very, very essential, where the value chain is completely digitized and it has to be integrated by means of the supporting methods and tools, which ranges from simulation, lifecycle management modules, manufacturing execution system modules, and lifecycle data-driven modules, which can span across various activities starting from product design, manufacturing planning, manufacturing engineering, manufacturing and services. Thereby, it can connect the two scenarios of virtual and the physical scenarios, and could enable value chain execution to a greater level. And the kind of skill set that is relevant in the context of this smart manufacturing systems is very essential. The one on the left with the blue font indicates the skill set required for the present scenario, and one on the right is with the black font indicate the skill set for the prior scenarios, wherein the higher levels of creativity and innovation is very important, and the decision making and the problem solving skills have to be elevated to deal with the complex scenarios. And also the cognitive aspect is very essential, because most situations for a problem, different solutions have to be identified very quickly, and we need to arrive at the convergence of solving the problem in terms of finding the most vital solution. That is again a very important skill set that is very essential. So definitely the role of technologies is very important in terms of executing the smart factory activities. And before we proceed with the discussion on technologies, and having discussed about some prelude for the smart manufacturing, and we discussed on the need and the emergence and the focus, and also the scenario of factories and the skill set requirement. Now, before we proceed with the technologies discussion, are there any questions at this stage which I can respond and proceed further? Are there any questions from attendees at this stage? From coordinator side, are there any queries in the chat box? Because my chat box is not concurrently visible to me in my screen. The coordinating officials, are there any questions in the chat box? Sir?
Sir.
Sir, are there any
Sir.
queries in the chat box? Okay. Till now?
I will check, sir.
Yeah, because it's
no,
not visible to
no,
me
sir.
in my screen.
No, sir, no queries, sir.
Okay, so
Please
let me
carry on,
ask
sir.
from let me ask from participants. Okay, so are there any queries from the attendees at this stage? Maybe one or two questions. Kindly feel free to interact and post your queries in the chat box.
No, sir. Right now there is no query, but very soon I will ask some question. I'm trying to connect.
Kindly feel. Yes, madam.
Right
kindly
now,
feel free to interact.
Right now I have no questions, sir, but I'm trying to connect with my subject. Actually, I'm from management faculty. So
Fine, madam,
we are
fine,
also doing like data analytics and
yes, madam.
these are things IoT. So
Yes, ma'am.
how we can connect all these things? So I'm connecting with you. Very
Definitely,
soon I will
definitely.
ask question. Yes.
Yes. Kindly feel free. And from attendees, so this kind of sessions, it should be interactive. So kindly feel free to ask the questions so that we shall try to understand the perspectives more effectively, and let us try to share our views and thoughts parallelly with the discussion. Okay. So let me just proceed with the discussion on the technologies. So there are like different technologies connecting the smart manufacturing and deploying a smart manufacturing system. Let us go one by one and discuss and try to have the perspective of those technologies. The first one, as we have discussed, the CPS, cyber physical systems, which forms the base, and it is something like a system. It's the base and the foundation for the smart manufacturing system, whereby it facilitates, it provides a kind of a typical environment which offers a real-time data collection, analysis, and ensure the transparency across various aspects of the executing manufacturing task. Just very, very important technology. And this is something like a concept map which I have taken from the literature, and I would like to present for the discussion. As we could see, there are like different modules in the CPS things, starting from the sensing and actuation module, the feedback system module, cybersecurity module, design tools and methods, and scalability aspects and validation modules. And also the application domains have been typically illustrated. And this provides a very comprehensive view of a CPS. And utilizing CPS is very, very essential for connecting a digital twin system. So let us just proceed about the connectivity with other technologies. Next one is about like data analytics, and in terms of typically handling big data. As we are aware, in the prior revolutions also, we had data analysis, where definitely the analysis of data is very essential to recognize the patterns associated with the data, the trends, the associations, and so on. So very important aspect is how typically we need to come out with the analysis. And the situation is that today, we need to deal with like big data, the scenario of big data, where the volume and variance of data are huge, and the role of analytics is very essential in this case, because the problem scenario will be on level 3, where the problem will be unique and the solution has to be unique, and none of the existing solutions may not fit with the problem. Then we could understand the role of the analytics. Typically advanced analytics, we need to take care, we need to deploy them where the scenario is highly complex, and we may have to deal with the scenario of big data. So this is something like a very typical scenario to be dealt with, and the role of analytics is very, very essential. And we take the support of AI tools in terms of like machine learning, deep learning modules also help us in a big way to deal with the challenges. Next comes the integration. One is the horizontal and this second is about like vertical. So horizontal integration is has its focus on developing and utilizing the core competence external to the organization. And the vertical is about like utilizing in-house expertise in terms of like varied functions, starting from product development to manufacturing, marketing, and so on. So the system integration has to be supported both horizontally and vertically across different levels of activities, starting from the shop floor, the operational aspect, then the tactical and the strategic strategic level activities also. And the role of lifecycle management modules is very important in this direction, where along with that, we take the help of IoT and iOS also. Then the role of additive manufacturing comes into picture, which is a transformative approach, typically in the manufacturing, where it provides like a digital perspective for design and manufacturing, whereby we could ensure the objects or the components are being created by material addition, which is totally opposite to the subtractive approaches we do. And here we try to typically add the material layer by layer, and we end up with the scenario of the fabricating the components or the products. Typically, this technology started with prototyping, where we can try to exploit the prototyping phase of product development because it consumed more time. Then came the technology of tool making using this additive approach by the term rapid tooling. And then it had been realized like rapid manufacturing, that is manufacturing end-use parts directly using the digital technology in line with the requirements. And based on the ASTM and ISO standards, all these terms are being unified with the term additive manufacturing. So there are like different technologies in additive manufacturing. Some technologies they utilize laser, and some technologies they don't utilize laser. And there are like different type of materials we handle. And there are like 7 basic technologies, starting from an extrusion type process polymerization, and sheet lamination, powder bed fusion, direct energy deposition, binder jetting, and metal jetting. The 7 basic technologies, and there are several advancements also have happened, but they provide a complete perspective for digital design and manufacturing without the requirement of a tooling. Directly from the idea or the concept, we can come out with the component or prototype or product within the shortest period of time. Thereby, we'll be able to compress the time and enable the concurrent execution of engineering activities in a very, very effective way. And this is something like a technology which has taken a lead among the industrial scenario and also the R&D organizations, where typically the advantages include the development of complex geometries, and also we can come out with lightweight geometries and the structures, near field requirements, and also those components which can fulfill the field conditions. And thereby this is possible with the optimal time, and thereby we'll be able to come out with lightweight structures as well more effectively. And this is one of the digital scenario for design and manufacturing, and it helps in a big way the industries to take ahead with the diversified requirements of the customers, and also to come out with the complex structures which are very difficult to be processed using the traditional subtractive approaches. And there are like different developments which have happened in this technology, because the technology is also called like 3D printing or 3D-dimensional printing, where we are able to print the 3-dimensional objects from the digital geometric models from the CAD data. Also, now we are moving to a scenario like 4-dimensional printing, where the components or objects, after being printed, they try to get assembled on their own in order to get reassembled, in order to proceed with the final assembly. On their own, they get aligned. Then we could understand the material technology in this context, which is a lot of developments have happened. And we go ahead with like using smart materials or like shape memory materials, which can help in this phenomenon of getting configured into an assembly over the time period. That is the essence of the 4-dimensional printing. So now a lot of research is happening on the materials development and also the technological aspects and the concepts which is related to the 4-dimensional printing, or which is also called as 4-dimensional additive manufacturing. Next comes the role of Internet of Things and Industrial Internet of Things, which are very, very essential technology, which are used in typical industrial scenarios. And there were like a lot of applications across diversified domains, starting from like manufacturing and going ahead with communications and automotive systems and energy systems, power sector, and so on. And we need to say that it's nothing but like all sectors, typically they go ahead with the implementation of IoT to a big way. And this is something like a very conceptual view of an industrial IoT, wherein we are able to understand that the deployment of the machines, machine tools, the robots, the sensors, the communication networking protocols, and embedded systems, all these entities have to be unified in order to enable the development of an industrial IoT system, which has to be configured in line with the typical industrial applications. That's again very, very essential aspect. Next, let us discuss about like immersive technologies like augmented reality and virtual reality. Of course, all of us may have some kind of an experience with regard to this immersive technologies. One such technology is augmented reality, which help us to have an interactive experience of a real world environment. And this is something like the typical devices being interfaced to the smartphone applications. And we could see this kind of AR device, which will help us in enabling a digital manufacturing scenario, where through an AR-based system, we are able to identify or refer the catalogs and the manuals related to the machine tools, or like quality related manuals, and also the other standards and procedures. So there is no need for like the manual documents, and they are being completely digitalized, and through an AR-based system, we are able to access those documents in a more effective way. And also this is being interfaced to a smartphone-based application. So we are able to track the maintenance log of the machine tools as well. And also it facilitates like remote monitoring of certain parameters also in a more effective way. Okay, so they help us in thing. Mostly AR helps in like the in-house operations, and it also enhances the workplace safety. Thereby, the workforce also feel some this safer working environment in the smart factories. The next one is something but virtual reality, which is for like remote operations, as AR is for like in-house operations. So virtual reality is something like it provides a scope for innovative solutions. And as typically the manufacturing systems are equipped with smart machines, higher levels of connectivity, data intelligence, and simulation tools. This is something like an overview of a VR-based system. so that the someone who has to understand the working mechanism of a system or maybe a product or the equipment can have the experience, the virtual experience of handling the particular equipment or the product or the system, which is no way possible because some kind of an application we could see the environment is totally not conducive to take up in the field visits. So understanding such scenarios in certain sectors is also made possible using VR-based systems. They help us in a big way, and it will try to provide a complete interactive experience, and also we'll be able to have a very clear understanding of the working mechanism of the products and the systems in a more effective way. So as we have seen certain technologies, and also we will go through further few important and other important technologies as well. And the role of the communication networking protocols is very, very essential in the context of smart factories, where we do have like IEEE based protocols which facilitate like low speed and low power communication, and Zigbee for medium range connectivity, and we do have like 6LoWPAN and Z-Wave protocols which facilitate the radio communication technology. And also we do have like ISA based protocols, and as we are all familiar, we do have like Bluetooth, and other advancements in terms of the wireless communication technology like NFC, near field communication, which also enable like the close proximity without any physical contact between the devices. And also we do have like object recognition mechanisms like RFID and other related advancements. And also we do have like reliable and lightweight cost-effective protocols like MQTT, and also we do have like COAP and XMPP and other protocols, which are very, very essential in terms of developing an architecture for a smart factory. So here, having discussed about certain technologies of the smart manufacturing and this protocols, there are like the typical applications for the smarter systems, wherein in the context of manufacturing, we do data tracking, which is very well possible through this RFID based mechanisms, which will help us to do diversified tasks across the industry in terms of like supplier related information, customer related information, product quality inspection, and so on. And also vehicle inventory management in order to reduce the excessive inventory related aspects. And another important application is predictive analytics, which is very important in the context of IoT automotive, wherein we typically have an algorithm that can help us to analyze the future outcomes of the component based on its performance. And also there are like several related applications in the context of automotive maintenance systems, wherein we go ahead with the developing dashboard indicators for vehicles, and which facilitates very cost-effective aspects. And also we take the help of proximity sensors and cameras, which we could very well see in the modern automotive systems. They help us in providing a safer driving and safer experience, and also the possibility of errors could be minimized to a greater extent. So the applications are diversified across the application domains. So having discussed about the technologies and the protocols and some of the applications, and before we proceed further with the other related concepts, are there any questions from attendees at this stage? Kindly feel free to ask.
I have one question. Sir, I have one question.
Yes, madam, please go ahead.
Sir, what is difference between augmented reality and virtual reality? Virtual, madam, I got it.
Yes, ma'am. Augmented reality is virtual reality is for remote operations, ma'am, and augmented reality is for in-house operations. Say, I do have a product or a system, and I would like to refer the manuals. Rather than having like physical manuals, I'll be having the manuals available in my digital AR system, so that digitally I'll be able to refer and they complete the history behind that product, operating the product and other related aspects. And the instructions are available in a digital form in the AR system through which we can refer, and it is something, it will replace many of the manual tasks, madam. Hope I answered your
Thank you,
question,
sir.
ma'am. Yes, ma'am.
Sir, yeah, thank you, sir.
Yes, madam. Any further questions from participants at this stage?
Dr. Ashima, madam, please ask. Participants, anyone having queries, please ask.
Sir, good evening, sir. I want to ask one question.
Yes, sir.
Sir, how is smart manufacturing incorporate in circular economy, sir? How we can work on reducing the
Yeah. It's a good question.
cost
Anyway, so
and
we
how
we are yet to.
yeah.
So we are
Yes,
just
please.
about to discuss the concepts of sustainable manufacturing also. So typically, the adoption of the technologies and the digitalization is very essential in the context of circular economy based systems also. So in the due course, we'll be proceeding with the discussion related to the sustainable manufacturing. As now we are progressing towards the fifth industrial revolution, the the technology integration is very essential in order to execute the activities related to different R's of sustainable manufacturing, starting from recycling, reusing, and many other strategies. They have to be supported with technologies. Technology integration is helping the execution of various reverse activities, and thereby the circular economy is being facilitated. And I'll be able to provide you more perspectives in due course.
Yes, sir.
Hope it's clear, sir.
Yes, sir. Thank you, sir.
Fine. Any further questions at this stage? Fine. So let me proceed, and you may feel free to post the queries in the chat box as well. And interimly, let us discuss further. So this definition of smart manufacturing, as per the NIST, National Institute of Standards and Technology, US, it implies it's a completely integrated, a collaborative type of manufacturing system which can respond on real time in order to cope up with the changing demands and the factory scenarios, and also across the supply network, and in order to fulfill the requirements. That means across the total value chain, this integration is very essential. And this is something like a comprehensive definition which conveys the meaning of smart manufacturing. And in this slide, we could just have a perspective on the adoption rates of various emerging technologies, and their further projections are also being shown. And we shall discuss some other related technologies also subsequently. So as we discussed with certain technologies and a few other emerging technologies also, they help in terms of the network optimization and the inventory optimization, which is very essential in terms of manufacturing, and the technology help us in a great way. And also developing cloud manufacturing and cloud servers, because execution of smart factory activities definitely requires the cloud server based activities and cloud manufacturing concepts. And so that is helping in a big way. And as we are aware, like the scope of blockchains, which also helps in dealing with the financial transactions and ensuring the integrity, and the concept of drones, they are helping in a big way in terms of enabling the execution of various activities in the smart factory. And also, it is interesting to note most of the technologies, they are helping us in taking ahead with precise components fabrication, where we could see the concept of the CNC machining, which can be enhanced with multi-axis machining in order to reduce the setup times and rework minimization and so on. And also we move to a scenario of like hybrid manufacturing, where these additive approaches along with the subtractive approaches could be done on the same machine with good versatility in order to manufacture parts with lesser waste. And the role of simulation tools also, they help us in a big way in order to optimize the products and validate the products and also enable the prediction science. Then the role of cyber physical production systems is also, because from CPS, we are moving towards like cyber physical production system, CPPS, because there are various other activities of manufacturing also need to be taken care, like in terms of materials planning, materials planning, then manufacturing control, and other related activities in terms of coordinating the spectrum of tasks across the manufacturing also need to be taken care. So that's the reason we move from CPS to CPPS. And the concept of digital twins, as we discussed, they are very, very essential. And for all typical machine tools and the process, we try to develop the digital twins, and they are helping to enhance the manufacturing intelligence, and it tries to take ahead with the developments in terms of the industrial scenarios. So having discussed about the technologies, there are like a couple of architectures being contributed in the literature. For example, when we refer the data analytics cluster, we could see the kind of correlation with the decision-making approaches, the role of machine learning modules, predictive analytics, and forecasting modules, and statistical process control. They also help us in a big way in dealing with the data analysis. And proceeding with the enabling technologies, if we could see, there are like several communication technologies and identification technologies, and we go ahead with the fusion in terms of sensors and embedded systems. They also help us in a big way, which are being supported with the hardware. The synchronization of the hardware and software systems is very, very essential, and the technologies integration is contributing towards the execution of smart factories in a big way. And there were like typical challenges in terms of the smart factory activities, which ranges from like recognition related challenges, and in order to enable a heterogeneous environment, how the activities could be synchronized, and real-time characterization and so on. And also a typical structure, it tries to coordinate the physical and the virtual devices which are being supported with the cloud and industry networked platforms. So the applications are diversified across different sectors, and they help us in a big way in terms of enabling real-time visibility and the providing platform for data analytics, collaboration, and so on. So having discussed about the concepts of smart manufacturing, and as I mentioned that the terms Industry 4.0 and smart manufacturing, they have certain synchronous goals, but also there were like certain operational differences between these two systems. Where in terms of origin, one is with regard to German industries and another one is the context of US, which I mentioned earlier. And the Industry 4.0 aims at the smart intelligent factory activities, and the smart manufacturing is about like stakeholders collaboration for facilitating broad adoption of manufacturing intelligence. In I 4.0 aims at the smart factory execution with the support of CPS and IoT. But in smart manufacturing, we go to a level of CPPS, and also from IoT, we get elevated towards the level of IoE, which is Internet of Everything, and so on. This gives you some perspective on the minor differences in terms of operationalizing an I 4.1 smart manufacturing system. And this is nothing but a typical architecture of a smart factory, wherein we could see the complete perspective in terms of different layers, starting from a terminal layer, cloud application, network, and physical resources. And they are being supported with IoT, industrial IoT, Internet of Services, and we do have cloud servers and networking and communication protocols and embedded systems. All these entities are very, very essential in terms of smart factory execution. So the architecture development is also very essential in the context of smart factory, and the benefits or advantages are diversified in terms of like financial and maybe like some certain environmental related aspects, and also in terms of like the improvements in terms of optimal utilization of the workforce and the man hours, and also the proportion of time that is being spent on training and so on. And the applications, a list of sectors are being given, and the observation is that these concepts of smart manufacturing need to be adopted by all sectors and all organizations and across diversified ranges, starting from large scale, medium scale, and even like small scale industries. They come under the implementation plan, and it is very, very essential. And there were like different challenges being faced by even small scale organizations in terms of this technology infrastructure development, but they are very well could be handled using clustered approach and developing a common facility, and thereby the organizations could proceed in a shared way, utilizing the facilities to a greater extent. So there are like different remedial measures to deal with the challenges, but the insight is that all organizations, they need to go ahead with dealing with the developments in terms of industrial revolution. That is more important aspect. So having discussed about the concept of like a smart manufacturing, let us now spend time on discussing the sustainable manufacturing, and let us try to discuss on the inferences. So the term sustainability has come from the United Nations Brundtland Commission's definition, where it implies meeting the needs of the present without the compromise on the future generations' ability to meet their own needs. That means the resources utilization have to be very, very optimal. And there are some of the important dimensions we call as three important dimensions. One is environmental, economical, and societal aspect, which is the triple bottom line aspect of sustainability. Okay, three important dimensions of sustainability. So these three important dimensions, like environment, economy, and society, are based on the protecting the planet and ensuring business prosperity and the people aspect, where the environment is more about taking care of the resources, utilization of resources in a more effective way, and ensuring compliance with the regulations and eco balance and so on. Whereas economical perspective is about creating new employment opportunities, product and process innovation, and so on. The societal aspect is about improving health, enhancing quality of life, the compliance with safety and ethical aspects. So this triple bottom line of aspect of sustainability is a very important concept in the sustainability theory. And naturally, it is more interesting to see all these three dimensions have connectivity with each other. Any kind of an improvement we do in one dimension will have its corresponding reflection in other dimensions. Let us take a very common example, like most of the industries, they work on optimizing the weight of their product. So typically, this weight reduction will reduce the emissions and the environmental impacts, the carbon impacts typically. So it's an environmental aspect. And the weight reduction will contribute to the cost reduction. It's an economical aspect. And implementing this weight reduction concept or this optimizing the weight requires the learning and the knowledge and the training and other related aspects, which enhances the quality of the human workforce. It's a societal aspect. Any kind of a typical real world application, if you take this kind of this triple dimensions concept will be fulfilled. That's an interesting aspect of the TBL approach of sustainability. And here, if you could see the sustainable development, it happens across diversified sectors, starting from manufacturing, and it moves to like architecture and the construction industry, the energy domain, agriculture domain, the housing domain, the transportation domain, and so on. But the key aspect is technology and the utilizing the creativity and innovation and educating and training is very, very, very important aspects. Some domains are left blank. The idea being there are many more emerging domains and they have to be encompassed in the structure. And that is the reason they are being left blank. That implies the application domains are increasing day by day. That is the significance of the sustainable development. So now if you see the evolution of sustainable manufacturing, we could see over the time frame from the traditional conventional manufacturing, we move towards like lean manufacturing, which is something like a waste reduction based aspect, trying to minimize the 7 forms of waste and producing to customer demand only and enhancing value addition from customer perspective. It's an incremental Kaizen based approach. From lean manufacturing, we have moved towards like green manufacturing, where it is an environmentally benign system. It's a 3R based system, like reducing, reusing, and recycling. Next comes sustainable manufacturing, which is an innovative system which is incorporated with 6 R's. If you see the additional 3 R's, they are recovery, reverse design, and reverse manufacturing. So this slide clearly represents the difference between a green manufacturing and sustainable manufacturing. Though they have certain synchronous concepts, but in terms of operationalization and in terms of the concept, there exist certain differences that is being depicted in this slide. And as I mentioned, the sustainable system go ahead with the additional 3 R's in terms of dealing with the recovery, reverse design, and reverse manufacturing. So now there are like different concepts and tools of like sustainable manufacturing. And one such important tool or the technique is called life cycle assessment, which is called as LCA, where the whole purpose is to find the environmental impacts or assess the environmental impacts may be associated with products or process or services or systems. Okay. So that is the essence of LCA. And LCA is an important concept in terms of the sustainable manufacturing. So LCA has to be done based on the standards. We refer ISO standards. Generally 14,000 series is meant for environment, as we are all aware. And there are 2 standards for referring LCA. One is with regard to 14040 by ISO and 14044 by ISO, which has to be referred for performing LCA. So the 4 important phases have to be done in sequence, starting from goal and scope definition, inventory analysis, impact assessment, and interpretation. So in goal definition, we try to understand the functional unit and the functionality of a product or the system. Because understanding the functional aspect is very, very important to ensure the determination of the environmental impacts. And typically, we should set the goals that why we do LCA. Maybe the customer is asking, the regulatory agency is asking, or maybe like we would like to do proactively. So the goal should be very clear. And the scope, are we going to do only within the manufacturing phase, or we are covering the materials come manufacturing, or across the entire spectrum, starting from materials, manufacturing, use, and end of life. Whether all these 4 phases are being encompassed, that is also very, very essential. So this is about the first phase. And the second phase is about inventory analysis. The term inventory has a different meaning in the context of like the sustainability, where it implies the consumption of materials, consumption of energy, and typically the consumption of resources. Wherein typically, if for performing LCA, we have a typical database, and the database has all related data and information related to the manufacturing process and methods. And we need to specify only the inventory information. Thereby, the module will perform the analysis to find the impacts. So there are like different activities, and typically we need to create the process model for in the context of inventory analysis. And the process model typically will have, from a 2-dimensional perspective, correlating the inputs and outputs. And from a sustainability perspective, we need to consider the impacts, because the relation between the inputs and outputs is contributing to the impacts. Likewise, we need to have a clear perspective. And the third phase is about impact assessment, where, as I mentioned, based on the inventory data and the correlation with the database parameters, the module will calculate the impact. And the LCA standard also varies from one location to another location across the globe. In the context of Europe, they follow CML method, and in the context of India, we refer, like in Asia and South Asia, we refer like eco indicator. And applying the method, there are like series of steps which will be done in the module, and accordingly the impacts will be calculated, and it will be correlated with the categories, maybe something like a health related or ecosystem related or resource related impacts and so on. And typically this phase help us in calculating the impacts. So generally any LCA study, we can come out with like 16 impacts are possible to be determined. And generally in the context of product design and manufacturing, 4 impact parameters are very, very essential for us, starting from like carbon impact, like sulfur impacts, nitrous impact, and energy related impacts. And the fourth phase, once we calculate the impacts, the next aspect phase is nothing but interpretation. That means we need to find the inferences, and we need to come out with what activities we need to do in order to minimize the environmental impacts. Thereby, we'll be able to make the product more sustainable and more environmentally friendlier. That is more important. And 3 important entities which are very essential are the material, product, and process. And the interaction between these 3 factors will help us in a big way. So as I have shown, this is something like a typical process model correlating the inputs and outputs. And beyond this, we may have to go for the third dimension also, like impacts. So how the relation between the inputs and outputs will contribute to the impacts, that also need to be considered. And there are like different life cycle stages we may have to go through, and accordingly we need to calculate the cumulative score for the environmental performance. And this is something like a model from the energy viewpoint. And this kind of energy models also need to be developed. So they will give us a complete perspective of whether the energy utilization is as per is at an optimal level, or maybe from a calculated level, because we'll be able to do some empirical calculation for this much input, output, this much input, this should be the output. If there is any deviation in terms of the output or in terms of the energy utilization in a relatively larger perspective, then we need to have a look on the various parameters, and this kind of the process models or the energy models have to be reviewed, and we need to validate them. That's more important. Okay. So there are like different aspects with the reference to operationalizing this LCA tool. As I mentioned, that 4 important tools are the phases are like goal and scope definition, inventory analysis, impact assessment, and interpretation. So before we proceed further, having discussed about some concepts of sustainable manufacturing and also the life cycle assessment, and are there any queries from participants at this stage before we proceed further? Any queries at this stage? Kindly feel free to interact and raise your queries or the clarifications. Officials, the coordinating officials, are there any queries in the chat box? Sir, are there any queries in the chat box?
Sir, I have one small question.
Yes, madam.
Sir, you said additive manufacturing, there are advantages, like
Yes,
less generation of less waste.
Yes,
can you give any example, sir, so that can understand more clearly?
Yes, madam. Maybe if you see in the context of traditional manufacturing, where with regard to any process you take, because there will be utilization of the auxiliary materials like coolants and lubricants and other related grease and other related entities we try to utilize. Whereas in the context of additive manufacturing, we don't go for utilization of any such auxiliary materials. When we try to provide the support structures, and the support structures could be very easily, very optimally we can provide, and we can remove after the process. So this gives a perspective of the lesser wastage And second aspect is nothing but in additive manufacturing, before we proceed with the actual fabrication, we'll be able to virtually analyze all the parameters, and we can optimize any or the material consumption in advance before we proceed with the manufacturing. Thereby, the waste generation could be optimized in additive manufacturing. Hope I answered your question.
Yes, sir. Yes, sir.
Any further questions? Okay. So as Madam also asked about this additive manufacturing and in terms of waste, there's something like I'm also thought of telling an illustration for sustainable manufacturing through additive manufacturing, where we could see the waste generation is lesser and the material consumption could be regulated and could be optimized. And the kind of the design freedom additive manufacturing offers is also at a greater level. And we could see the lightweight structures and the lattice geometries which are being created from viewpoint of this additive manufacturing is also excellent example for or excellent illustration for the sustainability, where we can try to minimize the environmental impacts. And in terms of mechanisms also, like the powder-based process in additive manufacturing, lot of developments have happened in terms of recycling mechanisms with regard to the powder usage. And also in terms of support structures, mechanisms have been brought into practice to enable lesser utilization of the support structures. And there were like a lot of scope for exercising this reverse processing mechanisms in additive manufacturing as well. Okay. So as I mentioned, in any LCA study, we are with regard to product design and manufacturing, we are concerned with the 4 parameters. One is based on carbon, second is based on sulfur impact, and the third one is about like nitrous impact, and the fourth one, energy-based impacts. These are very, very significant in the context of manufacturing. And I'll be able to show you 2 important modules of LCA. One is a product-based LCA and another one is a process-based LCA. So typically a product-based LCA will help us to find the environmental impacts in advance, and accordingly we'll be able to optimize the parameters before we proceed with the further phases of the product development. So in a LCA module related to product perspective, the inputs that need to be given to this module are the geometric model of a product, which contains all the complete numerical description of an object in terms of its size, shape, and other related parameters. Next, material related aspects, the type of material and the manufacturing process, and also the locational information in terms of manufacturing and user location. So typically, these input parameters will help to find the environmental impacts across the life cycle phases, starting from materials, manufacturing, use, and end of life. And across 4 important parameters, as I mentioned, like carbon-based, sulfur-based, the nitrous-based, and the energy impacts. And also, it is possible to compare the design alternatives. Maybe I can keep the process and the design same, and I can work with different materials, or I can keep the material and products design same, and I can work with different process. All these combinations are possible, and I'll be able to come out with the best alternative for the implementation. So all this combination and this analysis is possible in order to come out with a better alternative in terms of material, product, and process for going ahead with product development. The second module is about like process-based LCA, wherein from a typical manufacturing process, we'll be able to create a life cycle model for illustrative purpose. An FDM, metal extrusion type process of additive manufacturing, is being represented with the various modules of the system, starting from a heating module like a material feeding module, and the electricity and other power-based module, and the deposition module, and so on. So having defined this kind of a typical process-based model, and having provided the information, as I mentioned, in terms of the inventory parameters, the module will calculate the environmental impacts, and it's being shown on the right side. The 3 categories of impacts, the red one represent the health related, and the green ecosystem based, and the third is about like resource based impacts. So for every process, we'll be able to find this kind of impacts. And for illustrative purpose, I have taken a case of a gear for which we performed an LCA on the top left and then the top right across the different process stages of fabricating this automotive component. The D-impact parameters are being represented across the three categories, and the bottom left shows a typical process model being created for this particular component, which is fabricated using the additive manufacturing. And the bottom right represents the cumulative impacts. It is possible to aggregate all the individual impacts of the processing stages and to come out with a typical process-based impacts across these three categories. This is very well possible in terms of a process-based LCA. And typically, in the process-based LCA, it is possible to compare a traditional process with an additive process. Say, for example, like an extrusion type process, I do an FDM-based process. I can compare with one of the traditional process like an injection molding or a blow molding scenario, and I can find out which is something like a more sustainable alternative in terms of like material, product, and process interaction. That is possible. And this kind of information or the analysis, the LCA is also very, very important in terms of like sustainability reporting and other related initiatives in line with the regulatory agencies and the norms to be fulfilled by the organizations. And this additive manufacturing I have taken for illustrative purpose is that it is something like a technology which has taken a lead in the present industrial developments. And it has, as I mentioned, it started from prototyping and it had gone to a level of tool making and direct rapid manufacturing of induced parts. And also there are developments in terms of three-dimensional additive manufacturing and the four-dimensional additive manufacturing. And also another important domain called like designing for additive manufacturing. We call it as a DFAM because the designs need to be made compatible for additive manufacturing. So what are all those aspects? What are all the guidelines? What are all the methods? That is very, very important. And this DFAM is similar or analogous to DFME, what we have in subtractive manufacturing. This is again a very important domain, which is very, very essential in the context of making the design compatible for additive manufacturing. Okay, let me just quickly show you the case study wherein this additive manufacturing is being represented. This is something like we worked on with this kind of a rotary switch based product for a typical organization, and most of the components are plastic injection molded in this case. And this is something on the left side we could see the completed exploded view of the switch, which we could see in the panel boards and other related applications. On the right side, we could see some of the models of the components being developed there. And here we have gone for a complete customization module for this particular organization. This is something like for this organization, a customization module is being developed there, and wherein we will be able to present the complete product variants being manufactured by the organization along with their technical features. And as a customer, any one of the a product among the variants will be selected, and the complete exploded view will be presented to the customers. So they go component by component, they spell out the modification or the changes that are required, either in verbal form or in terms of like the uploading the drawings and other related aspects. So this will help us to systematically capture all customers' requirements, and a code will be generated for every customer requirement. And accordingly, we go ahead with some kind of a sorting algorithm to capture the commonalities among the different requirements of customers. And typically that will help us to minimize the assembly time and also the product development time. And we could see some of the customization modules being developed in line with the customer's preferences. It's something like an example for how this customization is very much possible in this case of the organizations, and where these technologies like additive manufacturing also helped us in a big way in terms of proof of concept establishment and other related phases. So for validating this proof of concept aspects, we have gone with the three-dimensional printing, and we could print the components or the prototype models before we go ahead with actual manufacturing and the component. And it's possible to observe the time consumed and the material consumption in advance, so that we can go for optimizing these parameters and we can try to develop the components in line with the requirements. And this is something like why the case I have taken for illustration is that there is nothing but a concept which gives a complete digital perspective of the various activities of product development And typically, it helped us, the customization module also helped the customers to effectively select and configure the designs based on their requirements. And maybe like another case study we did for another pump manufacturing organization, where typically we did for improving the functional performance or the maybe like the efficiency of a centrifugal pump being manufactured by the organization. These are the models of the impeller and casing being shown. And by varying the head and discharge values, it is possible to come out with the varied dimensions. And in this project, we had like two challenges in terms of coming out with the dimensional parameters or the dimensions in line with the varied requirements of customers. So once we specify the head and discharge, the it has to go through a series of steps to analyze the characteristic curves, and accordingly we need to come out with the dimensions. This is something like a time-consuming task. And when we do have like different combinations of head and discharge values, it has taken a reasonable amount of time to calculate or to compute the dimensions of the impeller and casing. So for which we developed a software support, which helped us in calculating the dimensions of the components based on the input values. And also another challenge we typically had is that in line with every head and discharge pair, the different dimensions of the impeller and casing are have to be derived, and it consumed time for every iteration. And we took the help of the parametric design approach in geometric modeling, and it helped us to set a baseline design, and accordingly the changes in the designs and the changes in the variations in the dimensions are being taken care, and accordingly the best design is possible to be arrived at. Multiple designs have been evolved, and the best design is being narrowed down, and the design is being taken further for analysis, and the optimization is being done. And accordingly, we went ahead with this kind of an extrusion type machine to fabricate the component. The one on the top is nothing but a digital file, and the one on the bottom is nothing but a fabricated the impeller module. And accordingly, we have taken ahead with the fabrication, and further we went for infiltration, and accordingly we were able to provide the required engineering properties on the impeller. So accordingly, the testing and validation is very much possible in this case, and it is an excellent application or the illustrative case for this kind of a digital perspective of the design and manufacturing. And this is nothing but the printing facility we do have in our laboratory, and with the corresponding dimensions. And we did this is something but the software interface. And the interface why I'm showing is that so a lot of this optimization is possible, and in terms of developing support structures, generating support structures, optimizing support structures, everything is possible in terms of correlating with the time and other related material related parameters. And these are some of the components being printed in our lab for some medical applications and some automotive applications. And we do studies jointly with the industries, and we did also life cycle assessment of those components, and we optimize the environmental impacts of the products which are used in automotive applications as well. Okay, so there were like having shown some of the case studies for the illustrative purpose, let us spend now some time on understanding the trends of the three-dimensional additive manufacturing to understand the essence of the three-dimensional additive manufacturing. We could see somewhere something like this 1980s, we could see the kind of a hardware and software being used those days for this three-dimensional additive manufacturing, where even the concept of computer graphics was not being established. Then later, they have gone with this extrusion type additive manufacturing, where the concept of computer graphics got established. And somewhere in 2005, we could see this kind of open source type of machine, which shows like collaborative environment, and they can print the components on their own. In the same time frame, we could see this kind of customization approach in the laser sintering process, a powder bed fusion process. And somewhere in 2008, we could see the idea of the self-replicating machines, the capabilities being enhanced, and a printing machine can print many of its components, and it can give rise to other printers generatively. The same time frame, we could see the kind of the printers used for printing the concrete floor, and where we could see this kind of a gantry robotic arm used in construction related applications. And the construction industry also utilizes this digital technology to a greater extent. And in 2009, we could see the idea of these printers being used in like personal applications, like kids, they want to print the toys of their choice. They pick the digital file, give to a machine, and accordingly the printer prints. And also in the food industry, the application is being implemented because in many of the pizza shops, we can see the 3D printers are being used and they deposit the food flour in a very precise way. So the applications are increasing. The technologies are helping us, starting from an extrusion perspective, powder bed fusion, polymerization, and binder jetting, and so on. And the applications, starting from prototyping, it got expanded to tool making and to direct digital manufacturing and personal fabrication, and is increasing at a greater level. So this scenario shows the perspective of this digital manufacturing and how it is helping us in terms of developing the applications in line with industrial developments and many more applications for this digital manufacturing has come. And that's the reason I have taken this additive manufacturing as an illustration for this smart and sustainable manufacturing. So now let me, having discussed about the concepts of smart and sustainable manufacturing with an illustration of an additive manufacturing, we could see how this technology integration is also helping the digital manufacturing being supported with sustainability concepts is helping in a big way. So now let me share a video file which shows the complete perspective of a smart factory and the related developments. Let me share the video file now for discussion. Just a moment. Let me just share the video file. Just a moment. One second. I hope the video file is visible to all participants. Is it visible?
Yes, sir. Yes, sir. Visible, sir.
Okay. Let me play the video file and explain to you.
Okay, sir. Okay, sir.
So in the first part of the video file, the scenario of manufacturing the cars in a particular automotive industry is being very clearly shown the various stages, and also we could see the robots which are being deployed in terms of executing the activities. Now let us see the digital scenario in terms of Industry 4.0. So the second part of the video file, clearly we are able to see the digitalization scenario in the manufacturing factory, where we could see the technologies like a collaborative type of robot, how it is doing coordinative activity with the human workforce, and big data monitoring, and simulation-based modules, and a typical powder bed fusion process for fabricating the tooling, and the role of analytics, AI/ML, and other related technologies also being very clearly indicated in the second part of the presentation, which gives a complete perspective of sir, any coordinators, could you please check to the interruption?
Please carry on, sir.
Yeah. So this second part, which clearly shows the kind of digitalization in the context of manufacturing, how the organization is able to deploy the technologies more effectively, thereby the complete digitalization is made possible. So that is something like an essence, which gives us a complete perspective of a smart manufacturing. And definitely in smart manufacturing, the concept of sustainability is very, very essential, where the lifecycle management modules and also lifecycle assessment tools also, they help us in a big way in terms of deploying the smart manufacturing systems in a big way. So now we are approaching towards the fifth industrial revolution, Industry 5.0, where the focus is on utilizing the human intellectual capability and sustainability and resilience in terms of developing a hyper connected factory scenario. From smart factory, we are proceeding to a scenario of something like a hyper connected factory, which helps us in a big way in terms of dealing with the challenges. Okay, so so as we discussed the concepts of smart and sustainable manufacturing, and we have seen a complete video file which gives us a perspective of this digitalized manufacturing. Now we shall spend few minutes for responding to your queries. So participants, any queries from your side, feel free to interact. So any queries from participants? Kindly feel free to
Dear
get
participants,
clarified.
dear participants, if you have any queries, please ask.
Anuradha Garu is asking to unmute her.
Participants, it's now time for queries. You can ask queries.
I think Anuradha madam is having a query, so kindly go ahead.
Yeah, she's asking for unmute herself. She's unable to. So please once check it out. Anuradha Garu wants to talk something, but she's unable to talk.
Okay, okay. She is in mute. Anuradha ma'am. Anuradha ma'am. Other participants, if you have any queries, please ask. Anyone for queries?
I think there is no question, sir.
Anuradha ma'am, she her message is still not unmuted.
Sir, I could see another question in the chat box. Meanwhile, I can respond to that question.
Yes, sir. Yes, sir.
The question is about there are huge manufacturing factories and upgrading them to smart manufacturing units will be very costly and complex. What is my view? They have asked. Yes, it's a challenging aspect, but generally, in line with the industrial developments, all organizations across diversified sizes and the scaling, they need to proceed with the technology developments, which will help them to develop a technological infrastructure. Thereby, they can respond to the varied requirements of the customers. So that is very, very essential. And also, there are like the kind of grants and from the ministry also for motivating the industries to adopt the technologies, and thereby the manufacturing GDP also could increase. That's very essential. Okay. Any further queries from participants?
Hello, sir. Good evening.
Yes, madam. Good evening,
Good
madam.
evening.
Good evening, madam.
So since we have discussed about the smart manufacturing, and we have seen that most of the times what we have all of the things are being taken care by the smart thing. Smart thing means that there is less effort by the human being. And whatever
Okay.
other things may be, I am more concerned about the involvement of human being. So
Okay.
since there are two things, one is human being and another one is the skill. One is manpower and another is skilled manpower. So how much this the jobs of unskilled manpower is endangered with the use of this smart manufacturing, and whatever we are discussing here, since it is requirement for sustainable innovations and sustainable developments and also for energy efficiency. But I just want to know that how the problem of this endangerment of jobs of unskilled person is will be handled. Can you comment on that?
Yes, ma'am. Yes, madam. Yes, ma'am. Actually, now the scenario is the functional profiles are changing, and definitely the upskilling is very, very essential for all. For all, everyone has to undergo upskilling programs. So, and definitely they have to equip skills related with their functional profiles. and many functional profiles are getting changed, and we have to go ahead with the developments. So the upskilling programs will help them to enhance the technological skills, and thereby they can go ahead with the functional profiles which are expected in the context of industrial developments. That will help them, ma'am. Yeah. Hope I answered your question, ma'am.
And there is one another question related to that. Since we are we are all aware of upskilling programs, but most of the population in our country, which is living as a labor, they are not aware of these programs. The educational institutions are working in this direction, but still I have a very less idea that how we can improve their skills. Although the government has developed the skill development programs for lower class also, but
Yes, ma'am.
I'm still concerned about their jobs or how they
Yes,
can
ma'am.
be upskilled. What are the
Yes, ma'am.
awareness programs which we are organizing for making them aware of the programs which are being meant for their benefit?
Yes, madam. Because there are like sensitization programs being conducted jointly by academic institutions and government agencies and also industries. That is one avenue. And the second thing, these small scale organizations also, they go ahead with a cluster approach. Maybe like 5 to 10 organizations put together, they try to come out with a common base, and they go ahead with the implementation. And definitely as a part of the deployment, they train their workforce, and they will get adapted with the changes. That is another solution where the cluster-based implementation also helping them. And as you have mentioned, there are certain challenges, and gradually we may have to overcome the challenges. We need to understand the developments, and accordingly, the skill elevation is also very, very essential, ma'am.
Okay, thank you so much, sir. Thank you.
Yes, ma'am. Another query I could see in the chat box. So the idea is that in certain context, we need to go for enhancing the competence, or say for example, we have certain legacy machines. Their connectivity and the interoperability and related aspects also could be enhanced. So there are solutions which are available to enhance the connectivity aspects, and the technological integration is also possible with the legacy machines. It's not the case of replacing the legacy machines, but whatever is possible in terms of elevating the competence, or the level of the upgradation is also possible. So exploration need to be done, and judicial decisions also will help to enhancing the legacy missions to connectivity based missions. Hope I answered the question given by an attendee. Okay. So any further questions from participants? So I posted my email ID in the chat box. You can feel free to write to me if you have any specific queries or clarifications or requirements. So before I hand over to the organizers,
it's
a pleasure.
Question.
Yeah.
In chat box, one question was posted. After scrap, is there any scope for smart manufacturing like that? One question was posted.
Actually, the decision of making it as a scrap is a judicial thing that need to be taken care. And say once it becomes a scrap, then we may have to explore the reverse options, as I highlighted in the context of sustainable manufacturing. And we can explore some components for like direct reuse, and some components for reverse cycling. And those 6R mechanisms will help to explore the further aspects of dealing with those components. That's reverse strategies could be explored. And another query I could see. So in Indian scenario also, there are different strategies being adopted for this Industry 4.0 based deployment. So it's a transformative approach that is agreed, but the capabilities and developing the technological infrastructure, it's up to the organization to ascertain the technological infrastructure requirements, and they may have to proceed with the technology based implementation. And the strategies though there are certain strategies available, but it is up to the organization to identify a particular strategy for developing the technological infrastructure that can help to deal with this transformation journey. Okay, fine. Any further queries from attendees before I hand over to the organizing team?
Any queries, dear participants?
Fine. So, so it's my pleasure that to be a part of this FDP program, and the purpose of this FDP and the short-term courses is that whatever the concepts being discussed that will help us to offer courses, or maybe if we are offering courses, it will help us to augment the concepts, and also it will help us to identify certain research avenues and some scope for taking projects jointly with industries. And this Industry 4.1 smart manufacturing is a very typical avenue which will help us to enhance these avenues, explore these avenues. And I appreciate the organizers. They have taken up a very relevant topic for the FDP. And I would like to thank all attendees of the session for your patient listening and the interaction we had. And I would like to thank the organizers for inviting me to deliver this lecture, to be a part of this FDP today. Okay, thank you all. My sincere wishes to all of you. Okay.
Sir, we are extremely thankful to you, sir, for the excellent presentation, sir. The session was also very informative and well structured, and provided very valuable insights about manufacturing, industry revolution, and latest developments in this manufacturing sector, sir. Sir, we truly appreciate your time, sir, and effort in sharing your expertise with us, sir. So thank you very much, sir. Thank you very much, sir.
Sir, there is one question I have seen in the chat box, that the launching of the multiple schemes and the adoption. Okay. So in this context, the adoption of the schemes, the stakeholders should have appropriate awareness, and that will help them to identify the appropriate scheme to adopt the technologies. One is the awareness, and second thing is, I think, but having a global perspective and global view also will help them to identify an appropriate scheme. I think that could help. So another question is about like molecular manufacturing concept. Yes. So the feasibility have to be analyzed in a detailed way, and appropriate studies could help us in taking ahead with the concepts. Okay, fine. I hope I answered to the
sir,
queries.
Ashish Kumar, sir. Ashish Kumar raised his hand. Sir, please. Sir.
Yeah.
Ashish Kumar, sir.
Ashish Kumar, sir, please unmute yourself and you can ask your question.
Or you may post your query in the chat box, sir.
Yes, sir. Actually, he has posted in chat box. Does molecular manufacturing concept feasible?
I have answered to that, ma'am, because it's nothing but only thing, some detailed feasibility analysis also need to be explored, and accordingly the appropriate decision could be followed up.
Yeah. Okay, sir. Thank you, sir. Thank you so much for the insightful presentation, sir. And the session was highly beneficial to all the participants also. And thank you so much for sharing your valuable expertise with us.
Fine, madam. Thank you all.
Thank
and
you,
okay, thank you all. Okay, fine. Madam, I'm leaving the meeting. Okay.
Yes, sir. Yes.
Okay.
Okay. Thank you all. Thank you.
Thank you.
Okay.
Thank you.
Thank you.
As we come to the end of today's session, I would like to thank all our respected resource persons for sharing their valuable knowledge and insights, which made the program both informative and inspiring. We sincerely appreciate the active participation of all the faculty members and your engagement as thoughtful interactions truly added the value to this program. With this, we formally conclude this program. We look forward to your continued presence and enthusiastic participation in the upcoming sessions also. Thank you for your cooperation. Thank you so much. And the session has been ended.
Again, tomorrow at 6 p.m. We can meet. Thank you.